conservation of angular momentum. The total angular momentum L of a system of particles is the vector sum of the angular momentum L of the particles. So the total angular momentum of the system equal to L1, L2, L3 plus NL equal to sigma I, Li from 1 to n. Now, let's do the derivative with respect to time t on both sides. This is the derivative of angular momentum. We look just when we put the derivative inside, we get sigma d dt Li. And the d Li dt equal to sigma tau I. And this is the total torque, sum of the total torque. And the torque can include two parts. One is external force torque, one is internal force torque. Okay. And we find out the sigma tau internal torque equal to 0. Why? Because the force always appears in pairs. Okay. And the torque we put together is 0. So combine these two, we get sigma external torque equal to dl dt. This formula is the angular momentum of a system particle. It's similar to sigma f internal equal to dp dt, the system linear momentum derivative equal to the sigma net force. Okay. This is the Newton's second law for rotation in angular form. The net external torque, tonic, acting on a system of particles is equal to the time rate of change of the system total angular momentum L. This equation, of course, have to refer to the same orange. Okay. In an inertial reference frame, it can be applied with respect to any point, this point, the reference point. In an accelerating frame, such as wheel rolling down a ramp, it can be applied only with respect to the center of mass of the system. Before we go on, we have some review. We see a position R equal to xi plus yj with a zk. If we dot R with I, and we find I dot I equal to 1, I dot j equal to 0, I dot k equal to 0, so R dot I equal to x. Same reason, y equals R dot j, z equal to R dot k. Now, following, if we have air I, we want to find the z component, which is dot k. Okay. Another formula is a cross b dot c. You can rotate, put a motor down with b cross c dot a, and then b turn back, c cross dot a. Okay, actually this is a matrix like ax ay az, bx by bz, cx. They can rotate. They get the same value. Now let's go on. The angular momentum of a rigid body rotating about a fixed axis. We look this is a rigid body. This is a fixed axis c. Okay, this is x, y. Oh, let's look at one point, delta mi. This point, its location is ri from O, and its angular momentum around this O is ri cross pi. This is ri. Velocity is pi. This should be perpendicular to the z-axis, perpendicular to its radius, right? The velocity. Okay. Now, pi equal to delta mi vi. Okay. I want to find the z component of this vector, lik. as we studied before, we just use this one dot K. And Li is Ri cross delta Mi Vi dot K. This is A cross B dot K. It can be rewrite at B cross C dot A. Okay? Now, that looks like this one. Suppose this is called a unit vector R perpendicular to the P. This is a radius, okay? This is units. Now look this one, okay? This is equal to Vi cross K. The magnitude is delta MVI. This cross K, okay, equal to this cross K equal to this direction. Clear? Now, Vi, this one. Z, this one. You use the right hand curve, you get this red one, or called R perpendicular. What is R perpendicular? Is a unit vector. It's a unit vector, okay? It's both, okay? In direction of the radius of the circular path of the nth mass element. This is R. This is unit vector, okay? And then this is a dot. So we take this out, and we find that R perpendicular dot I. We just learn this is a unit vector, this is Ri, this is equivalent to the component along Z R perpendicular the Ri. Actually, this is a number, because we'll call it R perpendicular I. This is a radius of this particle, okay, radius, okay. So Ri is a number, is a perpendicular distance between the ith element and xz axis, okay. Now, since Vi equal to omega Rii, this is Vi rotate equal to omega V Ria. So we put this inside, we get this one equal to delta M R perpendicular I square omega. Now, this one is the I's. How about the total? Number total Z is sigma Liz is sigma this one. And this omega is a constant. It's true for everybody. You take it out of the sigma. And what is this? Sigma MR squared. So this is the initial, angular initial around this axis Z. So we have Lz equal to Iz omega. Then we get L equal to I omega. This is the vector equation, okay? It has three components, okay? Conservation of angular momentum, okay? So far, we have discussed two powerful conservation laws: the conservation of energy, the conservation of linear momentum. Now, we met a third law of this type, the conservation of angular momentum. dl dt equals sigma tau external, okay? If no net external torque acting on the system, this equation becomes dl dt equal to 0, or L is constant. This is an isolated system, no contact with outside, okay, because this is 0. Okay. This result, called the law of conservation of angular momentum, can also be written as L initial equal to L final. Okay. If the net external torque acting on the system is 0, the angular momentum L of the system remains constant, no matter what changes take place within the system. L equal constant, this is an equation, vector equation. So it will have three component equation. They are independent with each other. If the component of the net external torque on the system along a certain axis is zero, then that component of the angular momentum of the system along that axis cannot change, no matter what changes take place within the system. This is a three independent component. Like the other two conservation laws that we have discussed, the conservation of angular momentum holds beyond the limitations of Newtonian mechanics. They hold for particles whose speed approach that of light, where the theory of relativity reigns, and they remain true in the world of subatomic particles, where quantum mechanics rules. No exceptions to the law of conservation of angular momentum have been found. When r smaller, inertia smaller, so the angular velocity should be larger. And also the gravitational potential transfer the kinetic energy. So that's why it's wrong.
As the marbles
the omega
approach
gets
the bottom
bigger
of
and
the funnel,
bigger.
their radius of rotation decreases. As the radius decreases, the rotational velocity increases, conserving angular momentum.
This circular train track rotates freely on a bicycle wheel bearing. After this wind-up train is released from rest, the train moves clockwise while the track moves counterclockwise. The angular momentum of the system, which was initially zero, is still zero. When the train runs down, both train and track slow down and stop. This bicycle wheel rotates freely on a bearing support. An outer metal frame also rotates freely on a separate bearing. A spring-loaded brake attached to the outer frame connects the two so that they rotate together. We'll tie the brake back with a string so that we can spin the inner wheel. Then we'll burn the string. When the burning string snaps, the brake clamps the frame to the wheel, and they spin with a rotational speed that is less than that of the wheel alone. If we increase the mass of the outer frame and repeat the demonstration, the final speed is even smaller than before.
We now discuss 4 examples involving this law. The spinning volunteers. You see this guy sit in the chair with 2 dumbbells. Is there the force? Yes, gravitational force, and the chair, normal force. But these 2 forces without any torque around this axis because they parallel, okay? At the beginning, we rotate it. Okay, it has an angular frequency. If he moved his hand in this way, the inertia gets smaller. So by the conservation of angular momentum, the final velocity, angular velocity, should increase. In this sigma tau, external equal to 0. So IFI equal to IFFI. Okay, if the I decrease, the frequency must increase. Okay, okay, we see this one.
You've probably seen an ice skater perform a spin. We'll use this rotating stool and a pair of handheld weights to demonstrate the same effect. After a person holding the weights out at arm's length is spun, she rotates at a constant angular speed. When she pulls the weights closer in, her angular speed increases. Moving the weights back out slows her down. This animation shows the action from above.
Two, the spinning board diver. You see the Olympic race. You look at this point, center mass is parabolic, okay, like a single particle. And you want to do some action, you have to tuck your body. So why? Because in this case, the inertia is smaller, then omega can be larger. When you go diving in the water, you need to stable, so you have to open layoff position. Okay, the center of mass follows a parabolic path. Okay, referring to the center mass, because all the torque equal to zero, you have a gravitation force, but towards the center of mass, the torque is zero. So it's air angular momentum constant. 3, spacecraft orientation. In spacecraft, we have a flywheel, okay? When you want to adjust the location of the spacecraft, we rotate the flywheel. Why? Because this is an isolated system. The total sigma external torque is zero. So its angular momentum conserved, which is equal to I spacecraft, omega spacecraft plus I flywheel and angular velocity flywheel. Okay? We cannot, because originally the angular momentum is zero. And it conserved, so this one equal to zero. And then we get the omega spacecraft equal to minus the ratio. This is given, this is given, this we can control. In this way, if we do the integration with time, we get the delta theta spacecraft equal to minus this kind of the flywheel's angle. We can adjust the delta theta flywheel to control the spacecraft's rolling.
This man is sitting on a stool which is free to rotate. We'll give him a long bar with heavy weights on it. When the bar is rotating in one direction, he rotates in the opposite direction. If we move the weights further out on the bar and repeat the demonstration, will he now rotate more, less, or the same amount as before? He rotates more than before. This animation shows the motion from above.
This large metal disc is free to rotate on a bearing. A pair of smaller discs is attached to the outer edge. They can be released from the larger disc by pulling a trigger in the back. The large disc is spun by pulling on a cord wrapped around the axle. When the small discs are released, they will fly out on cables attached to a separate bearing. Here's what happens when they are released. The large disc stops, and the small discs revolve at high speed. Let's watch that in slow motion. What will happen if we add extra mass to the smaller discs and repeat the demonstration? Now, the large disc spins backwards.
Four, the incredible springing star. When the nuclear fire in the core of a star burns low, the star may eventually begin to collapse, building up pressure in its interior. This collapse may go so far as to reduce the radius of the star from something like that of the Sun to the incredibly small value of a few kilometers. The star then becomes a neutron star. Its material has been compressed to an incredibly dense gas of neutron. During this shrinking process, the star is an isolated system, and its angular momentum L cannot change. Because its rotational inertia is greatly reduced, its angular speed is correspondingly greatly increased to as much as 600 to 800 revolutions per second. For comparison, the Sun, a typical star, rotates at about 1 revolution per month. Sample. Figure A shows a student, again, sitting on a stool that can rotate freely about the vertical axis. Okay. The student initially addressed is holding a bicycle wheel whose rim is loaded with lead and whose rotation inertial I wheel about its center axis is 1.2 kg/meter squared. The wheel is rotating at an angular speed omega wheel 3.9 revolution per second. As seen from the overhead, we see from the top. The rotation is counterclockwise. What this means it's positive number. The axis of the wheel is vertical, and the angular momentum L width of the wheel points vertically upwards. See this one. The students turn inverse the wheel so that, as seen from the overhead, it is rotating clockwise. That means omega is negative number. Its angular momentum is then minus L wheel. The inversion results in the stool and the wheel center rotate together as a composite rigid body about the stool's rotation axis, with rotational inertia IB 6.8 kg/meter squared. The fact that the wheel is also rotating about its center does not affect the mass distribution of its composite body. Thus, IB has the same value whether or not the wheel rotates. Now, we rotate this up. Now it's going down. Okay, it's going down. And then the student wrote with this system. With what angular speed omega b, and in what direction does the composite body rotate after the inversion of the wheel? Originally it's going up, now it's turned down, and then it started to rotate. I want to find the angular speed and the direction. We know that's one. In this case, you have a gravitational force, have a normal force from the stool, but all these force does not have torque around this axis because they are the same parallel. So in this case, the angular momentum is conserved, and that means L beach final plus wheel final equal to L beach initial plus wheel initial. Now we put this number inside. This is angular momentum conserved before, after. Okay. Now let's book this one inside. The final angular momentum of wheel is equal to minus initial wheel because you turn around. Okay, and this initial the stool is 0. Okay, and I want to find this one. It's very simple. So we put this one equal to 2 is y. That's very simple. Okay, and when you write it out, what it is IB omega b. This is a 2I wheel omega wheel. Okay, and we find the angular velocity omega b equal to 2I wheel. So when you put a number inside, we get a number 1.4 revolution per second. Sample. In the overhead view of the figure, 4 thin uniform thick, this is 1, 2, 3, 4, each of mass big M and length d 0.5 meter are rigidly connected to a vertical axis. This is the vertical axis, okay, to form a turnstile. The turnstile rotates clockwise, that's negative number, okay, about the axis, which is attached to a floor, with initial angular velocity omega I equal to minus 2.0 radians per second. A mud ball of mass m equal to m over 3 and initial speed 12 meters per second is thrown along the path, shoot, and stick to the end of the one rod. What is the final angular velocity omega f of the ball turnstile system with ball stuck here? We look at this. This is sigma tau external equal to 0. Do you have a force? We check. When you hit this one, we do have a force. Okay, acting on this one, the gravitation force, whatever. Okay, and then towards this axis, these forces torque is 0. Okay, so the totally sigma external torque equals 0. Then the angular momentum of the system conserved. So then we write it detail. Initial, final. Okay. Final, we have two. One is the turnstile, one is the ball. Initially, you have two. One is the turnfly and the ball. And we write it down. Okay. Look at this one. The hit here. So this is the R, and its P is MV. Now we see, what is this? What is this? This is a R cross P. R cross P, which is outward from the surface. What is the angle? Now this is angle. RP, this is 60, this is 90. So this is 60 plus 90, 150. Okay, whatever. So D is R. P is MVI. Angle is 90 plus 60. So this is cosine 60. Okay. And we see this one, final. This one, we can find it. This one we want to find. This ball, initial, this is very simple, is mr squared, md squared, right? Yeah. So let's see initially. Initially you have rotate m versus I. And this one you have a d PMV cosine 60. That's all. But this is each one you have a 4. Each one is md squared over 3. Okay. What is this? This is stuck here. So that's equal to md squared. And this one is 4 md squared over 3. This one you have calculated. Okay. This one is given. This one is fine. So finally, we find omega f equal to 0.80 revolution per second. This is a positive number. What this means? That means after the hit this one, the rotation turnaround is counterclockwise.